Video 14 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is the Hermann-Feynman theory. We want to look now at a Hamiltonian which depends on some external field like the Hamiltonian we have derived in the previous chapters. And let's assume that we know the eigenfunctions of this Hamiltonian, which of course then also will depend on the field, and the corresponding eigenvalues, which means we know the solution of this Schrödinger equation, Hamiltonian, in the presence of fields. And we also assume that the eigenfunctions are properly normalized to 1 for all values of that field. What we want to investigate is now expressions for the first derivative of the energy with respect to a component of this field. So we take the derivative of the energy, meaning the eigenvalue of this Hamiltonian, with respect to one of the components of the field. And the energy, of course, we can calculate as expectation value of the Hamiltonian with its wave function. And so therefore we take the derivative of this expectation value with respect to a component of the field. Now the expectation value, of course, is an integral over the position of the particles which the Hamiltonian describes. So that's an integral over positions, whereas here we take the derivative with respect to a component of the field. So that's different variables, and therefore we can interchange the integration here in the Dirac notation and the differentiation. So if you do that, then we have to take the derivative of what is underneath the integral, and underneath the integral we have a product of three things. We have a wave function, we have the Hamiltonian acting on this wave function, and then we have the wave function complex conjugate. So we have to use the product rule, and since it's a product of three quantities which all depend on the field, we get three terms. And I've written it here in the first term. I take the middle one, so I have the derivative of the Hamiltonian, and you can see I switched the notation from these total derivatives to the partial derivatives because the Hamiltonian, we have the expression as we derived in the last section, and it explicitly depends on the field. So here we have the expectation value of the partial derivative of the Hamiltonian with respect to this component of the field. And then in the next two terms we have the derivative of the wave functions. A here first in the bra, which means the derivative of the complex conjugate of the wave function, and here in the ket. Now, we know the solution of this Schrödinger equation, meaning of the Hamiltonian with a field, and we know if the Hamiltonian acts on the wave function, we get the corresponding eigenvalue on the wave function back. So we can use that now in these two terms, where here we have the Hamiltonian acting on its wave function, or here the Hamiltonian acting to the left on the wave function in the bra. And in both cases we get the energy. Here we get we can just use this one, and then because the energy is a constant, take it out of the integral, which gives us this here. And in the second case we'll move the Hamiltonian, because it's a Hermitian operator, into the bra. Then we can let it apply to the wave function, which gives us the energy times the wave function. Then we have to take the energy out of the bra, and in principle we would have to complex conjugate it, but since the energy is a real number, we just get the energy back, and then we have this term. Now in the last step what we can do is interchange again differentiation and integration. So we can sort of go the step back and take the derivative out again, here out of the bra, and there out of the ket. And remember, I mean, this is the product of two terms, so we use the product rule, but now in the inverse, the opposite direction, so that what we get is here is the energy multiplied with the derivative of the norm of the wave function. But we start out with saying that the wave function is properly normed for all values of the field f. It's always 1, meaning it's a constant, and therefore this derivative of the norm is going to be 0. And for any value of the field, and we are left with that the first derivative of the energy with respect to a component of the field actually can also be calculated. It's just the expectation value of the corresponding derivative of the Hamiltonian with the wave function. Now let's look at this derivative of the Hamiltonian a bit more. And actually I want to call this derivative P. I mean, this is going to be an operator, and I want to call this operator P to associate it with the fact that for properties, because we will see in later chapters that we can define many properties as derivatives of the energy with respect to some components of some kind of field. So in order to make this association more clear, I call this operator P. Now in the last chapter we have seen that the Hamiltonian, in the presence of electromagnetic fields, there will be terms linear in the field and there will be terms quadratic in the field. And I introduced the notation with where we split up these first order linear terms in the field and second order terms quadratic in the field in, of course, components of the field and an operator which then only depends on or only includes operators related to the electrons, like position vectors or canonical momentum vectors. And those are called O. And O with the superscript F if it was linear in the field, and O with two Fs in the superscript if it was quadratic in the field. Now, if you don't, and of course, there are all the terms, the kinetic energy and the electrostatic potential for the electron-electron interaction and the electron nuclear attraction, all these terms which are not dependent on the electromagnetic fields, external electromagnetic fields. So if you take now the derivative of this Hamiltonian with respect to a component of the field, all these constant terms, of course, disappear. And from the terms which are linear in the fields, then taking the derivative, only the operator depending on the coordinates or position vectors and canonical momentum vectors of the electrons remains. And from the terms which are quadratic in the field, if I take the first derivative, I still have a field left. So that gives me this. So I can write this operator P obtained by taking the first derivative of the field-dependent Hamiltonian in two terms as an operator which is independent of the field, which are called P zeroth order, and an operator which is still linear dependent on the field because we have terms in the Hamiltonian which are quadratically dependent on the field. Right. Often we are interested in the derivatives of the energy with respect to components of the field, but evaluated at zero field strength. To indicate here. So, which means that if we then evaluate this expectation value at zero field strength, that of course means we have then the unperturbed wave function evaluated. I mean the wave function at zero field strength, which we also could call the unperturbed wave function. And then we have to evaluate this derivative of the Hamiltonian at zero field strength, which means that what is left from this operator here, which was the first derivative of the Hamiltonian respective field, is just a term which is not dependent on the field any longer, P zeroth order, also something called P. And that is called the Hermann-Feynman theorem. Hermann-Feynman theorem establishes an equivalence between a first derivative of the energy of the system and an expectation value of an operator which is obtained as the corresponding first derivative of the Hamiltonian. And this will become very useful later on. We should note that in the derivation of the Hermann-Feynman theorem, we did not assume that we have solved the Schrödinger equation for the system without the field. We assumed that we know the solution to the Schrödinger equation in the presence of the field, but actually not necessarily knowing without the field.